Morning, guys. Today we continue with rectilinear motion, but then in this case we are looking at erratic motion, or we can call it changing motion. Remember, the last videos that we did were on continuous motion, even though this is still a motion in a straight line because it's rectilinear motion, but now the motion is changing here, meaning the relationship between parameters of kinematics changes, right, as the motion continues. So we are saying that if an object has erratic or changing motion, its position, velocity, and acceleration cannot be completely defined by a single continuous mathematical function. Instead, a series of functions are required to specify the motion at different time intervals. So that means here now, if my motion is changing, I can't use one continuous function, because let's say now for the first half of the motion, the relationship between position and time is linear, right? And then now at the last half, it's parabolic, right? So that means that now I can't use one continuous function because this function changes, meaning the relationship between position and time changes, right? So that's why I cannot use one specific continuous function. I have got two. So we are saying that for this reason, we make use of graphs to define the motion. So that means here, instead of just one continuous mathematical function, instead a series of functions are required to specify the motion at different time intervals. So here I will require a series of functions instead of one function, and then also at different time intervals. And for this reason, we make use of graphs to define the motion, so that our motion, we can divide it in time intervals. It's going to be easier for us to see it when we use the graphs, because we can see the relationship where it changes. And then also, we do not really necessarily need to know where it changes. The more partitions we do, the more accurate we get our second graph that is going to be derived from the first graph. So that's just the case here. We just need to show this in terms of a graph because it's easier for us to separate it into time intervals, right? If a graph relating any two of the parameters, position, velocity, acceleration, and time can be drawn, subsequent graphs relating others can be derived from it knowing these relations, right? So we know these relationships between position, time, and velocity, acceleration, velocity, and time, acceleration, position, velocity, and the derivative of velocity. So that's just the case here. We see these relationships. Then knowing these relationships, if let's say I can draw a position time graph, then I can get my velocity graph, because my velocity is just ds over t. So I take my slopes at different time intervals and then I construct my velocity. Same thing, if I have my velocity, I can get the acceleration graph, because the acceleration graph is just the slope of that. So I take subsequent slopes to get my acceleration, right? So this is your erratic motion, changing motion. We have to show it in a graph, divide it into time intervals, take the derivatives and get other graphs, right? Or take the integrals, because it depends, because if we are coming from velocity to position, we need an integral, right? But then if we are going from position to velocity, we need a derivative, because remember, this is how we reverse a derivative into the original function. For me to get an original function, which is position, I would take an integral of my v graph, right? So that's just the case there. Let's see if maybe now for the first part we are given a position time graph, right? Sorry about that. Let me just try to draw it nicely. So we get our position time graph. Right, and then in this case, we know that what happens is that we have, let's say these are our x's, and then let's assume that, okay, let me first finish up. That is that this is your time in seconds, then this is your position in meters. And then now let's assume that the graph is gonna take this manner. So this is the relationship between position and time, right? So let's say the entire path will take that relationship, right? So you see it starts looking like it's linear, but then you see here it's kind of parabolic or cubic, but then doesn't really matter. So which means that here I cannot use a single function to define this entire path, right? So what we can do is we can separate these into time intervals, right? So I will separate these. Let's say here I have my t naught, and then here I'll have my T1, and then here my T2, T3. So the closer these are together, the more accurate my velocity will be. So T4, and then here I got my T5. Right. From there, let us trace these, something of that nature. Same here. Right. And then that's just the case here. And then this is our maximum point here. Right. What I want you to note is that always in our maximum point, the slope is 0. Please remember that, because we know that that's just a horizontal slope at the maximum. And we learned this from the absolute value theorem in mathematics. Right, so we have that as the tangent to the max. So this is where your slope is equals to 0 and your velocity equals to 0. Because remember, we said v is equals to ds dt. Right, and then in this part right here, we can say v is equals to 0. And then looking at other slopes, for this last part here, the slope is going to be something of this nature. Right. And then for the other part, which is this one, the slope is going to be, so because this is where it touches, so it's going to be something of that nature. Right. And then for this one, it's going to be something of this nature, because this is where it touches. And then for this one, it's going to be something of this nature, that's where it touches. Sorry. Okay. Why doesn't want to stick now? Okay, that's fine. We're gonna leave it like that. And then the second one, it's a little bit too steep to be accurate. Okay, I can put it that way, it's fine. And then for this one, okay, a little bit inaccurate. Okay, that is fine. I can assume that I can live with that. I can live with that. Okay. Right, so that is just the case there. I can live with these right here. Let us trace these velocities now. So here you have your v naught. Here you have your v1. Here you have your v2. And remember, your velocities are just the values for your slope here, or the function that you get for the slope, right? And then here you got your v3, and then here you got your v4, and then here you got your v5. And then here you have your, actually, what happens there? Oh, there I didn't have a velocity. So there's no velocity for this part. This is instead v4. And then I got my v5. Right, so I have all those velocities. So to construct another graph, which is just a velocity position graph, I just take those slopes and then put in points here using those slopes there. So it's a velocity time graph. Right, so your velocity time graph, same things. We're gonna have the slope here, and then it's gonna go like that. Right, so okay, cool. Let me just label it. All right, so let's see here. If you look at these values here for your velocity, your first value is a positive slope, right, which is a little bit more steep than the other lines here. And then so you have a positive number here. You don't have a 0 number for initial velocity because it's a positive slope. Remember, positive slope, negative slope, and 0 slope, undefined slope. Right, so I've shown you positive, negative, undefined, 0. These are all your slopes here, right? So let's see here. The first one is positive. This one is positive, but then slightly less than this one, because this is not too steep as this one. This one is more steep than that one, right? So let us do that. First of all, I'll have a positive value because it's a positive initial velocity somewhere there. the other one is less than at T1, it's less than this one because it's a little bit less than this one and it comes to steepness. So it's going to be something of this nature. I think that was too much, but somewhere there. Right, and then we come to the second part here. So for this one, it looks like I drew it a bit wrong because this one is a little bit less than this one when it comes to steepness. Let us try to show it because I believe it's wrong when it comes to that slope that I drew. This is the point, right? So to draw a line that touches only there, okay, I want to be fair. This looks like something of this nature. If you look at this one, it's more steeper than this one because if you were to trace it up, it's going to go up, up, up like that. So you see, it's a little bit steeper than this one. So this one goes down a little bit if you look at it here because it has to touch it exactly then. So this one is less than this one. When I look at the second one, this one is less steep than this one. So this one is also less than V2, right? So V2 less than V1, V3 less than V2. And then I come to this point. This is where I have a 0 velocity. It's a time that I didn't note here, but somewhere here in between V3 and V4, I have a 0 velocity. So it has to cross my x-axis. And then at V4, I have a negative slope, right? So that my velocity is going to be negative here. Also here, more negative because it's a little bit more steep than this one, right? So trying to show this for my V2 less than this one. Right, little bit less, and then V3 same thing, little bit less, and then now there comes that V that is in between V3 and V4, but V4 is negative somewhere here, V5 is more negative somewhere there, right? So if you look at it, that is just the case there. So we can say our graph is gonna look something of this nature. Okay, I'm trying to see if I can't make it into a curve. Okay, I think that is better. I don't know, but it's a little bit better than the rest things that I did, but that's fine. So let us assume that also this thing passes here, but as long as we know it's less than that one, right? Because that's the important thing here, right? Also that one, I will assume that it's somewhere in there along that line, right? Right, so let us assume this is going to be our velocity, but we see where it's coming from. Where I have 0 velocity, also here 0 velocity. Where I have a negative slope, negative velocity. Positive slope, positive velocity. So if the slope keeps on decreasing, my graph also decreases. If the slope was increasing, the graph was going to increase. So please remember that. And I have an initial value for velocity, which is positive, because the slope there is positive, it's not 0, right? We are done with this thing, then this is going to be your velocity at different time intervals, right? So you can show that using this is at certain time, this is at certain time, this is at certain time, at certain time, and at certain time. So those ones are going to be your T1, T2, T3, and then here I got my T4, and then here I have my T5, and then this is T0. I have the velocity from the position time graph. So this is the velocity time graph. But remember something now. I'm going to talk about acceleration. Acceleration equals to dv dt. Meaning from this equation, I can get my acceleration by just finding the slopes, right? So the first slope here, I can ask, because this is a maximum, this graph starts here and it goes down. And also if you look at it here, the line that touches only this at one point here, it's a horizontal line, right? So this is going to be your A1, right? First acceleration equals to the slope. Second acceleration equals to something of this nature. Right, let me just try. Right, and then third. Okay, fourth. right? Some stuff I'm just gonna leave them as inaccurate as they are because it's gonna waste a lot of time. Right, so see here it's changing the curvature, and then here I'll end up having another one which is something of this nature. All right, so we see the acceleration, the gradient keeps on going down, 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 and then down. Right, so it keeps on going down, down, more, more. So it keeps on getting more negative because it starts at 0 gradient, and then it gets more negative, more and more negative, because it becomes more and more steep as we go down here. So that's just the case here. So your acceleration, negative slope means negative acceleration. Remember that. So here is your a2, your a3 is just the value of the derivative, a4, and then here you get your a5, a2, 3. What? Oh, this is a0. This is 1. This is 2. This is 3. This is 4. This is 5. Right. Now that we have all those accelerations, let us draw the acceleration time graph. So we have our acceleration time graph taking this shape. All right, and then here we get time in seconds. So acceleration is gonna be, let's come here. First of all, the first point is 0 slope. Remember that at t0. So that was the gradient here. The gradient is 0. So the gradient keeps on decreasing, getting more negative, right? And then now, if you look at it here, this is way more steep than this line and then this line. So it seems like it's getting down a bit, and then somewhere at this point, it wants to change the orientation, right? So it's going to change orientation here and then also here. So it shows that it's getting more negative, and a little bit less negative, and then less negative in that case, right? Oh, actually I drew these lines of mine wrong, because if you were to draw the slope here, you would see it's a more steep, and then also for this one it's more steep than the others here, right? Not sure if I want to fix it though, but please note those things here, because I don't know, I keep on drawing it very wrong, but it's a little bit more steep. This line is supposed to be in this angle a little bit less, so that it touches this line only at that point. Also, this line is supposed to be in this angle a little bit, so that it touches this line only at that point. So we can see that the gradient, it doesn't change its orientation, it keeps on decreasing, right? So that's just the case here. So it's gonna start at 0, and it's gonna keep on decreasing, something of that nature, something of that nature, something of that nature, and then something of that nature, right? So I'm gonna say 0, 1, 2, 3, 4, and then fifth one there, somewhere there, right? I'm gonna assume that is our acceleration. All right, let us assume that those points are correct. It's fine, I can fix them. So it's decreasing, keeps on decreasing, keeps on decreasing, keeps on decreasing. 1, 2, 3, 4, 5. Right, that is fine. Now I can say these are my partitions here, right? So this is at t0, then the t1, t2, and then t3, and then t4, and then t5, right? But what I want you to note is these relationships now. So you got your, this one is an acceleration time graph, right? So we get the acceleration time. Right, so yep, I think those are just the basics for your erratic motion. As long as you know that your motion, you can show it in terms of graph, and then you partition it into time intervals, and then you take the derivative at certain time intervals to get the other values, right? So now if I were to come back from this one, from velocity to position, then I would take the integral, right? Because remember, you just take the integral for you to go back, right? So this is just the case, but I will just leave it here, and then we can talk about when you're given the acceleration in terms of position and also the velocity in terms of position. But for now, this is the introduction to erratic motion. Right, I'll see you on the next video.